as refractors, as we want to build bigger and bigger telescopes to look at dimmer and dimmer objects, these refractors got absolutely massive, unwieldy, and there were all sorts of problems that came along with that. And even with smaller ones, chromatic aberration is one of them. So this is kind of a unique problem to the refractors. So this is because the lenses bend the light, bend different wavelengths of light differently. So what's happening here is this light is being split into, this is an exaggeration, but it's being split into red, green, and blue. And that is just a cause of this lens, right? So that is being split, and as a result what you get is this kind of color, like this should be black. What you're actually getting, especially around the edges, is this kind of, this color bleed that's kind of happening. And that is chromatic aberration. So we've of course found ways to try and make this better, and by we, I just mean astronomers in general. So we can use these. So an achromatic doublet, for instance, tries to fix this up a little bit here. It's not perfect, but that's okay. So you can see what it's trying to do. And the more lenses that the more correcting lenses that you put in, the better it gets. We'll talk about that in a second. But yeah, you can see what's happening here is it's basically trying to get this light back into a path where, at the focal point of where you're looking with your eyes, that it will actually just bring those colors back together again. So, yeah. So basically, the more lenses, the better. But of course, more lenses, it requires more. You gotta add a little bit more time and effort to manufacturing them, so they get more expensive. There's also the added weight. Weight becomes a big thing. So glass, it's fairly heavy, right? Yeah. So it takes a little bit more work and a little bit more money, but you do get this nice fine focus point that you can then look at your objects with, and you remove a lot of that chromatic aberration. And it's worth mentioning that refractors are they're a common telescope. I mean, I think most people tend to stick with the reflectors because you get the big light bucket, kind of thing. But refractors can give you some very, very nice views. They're very good at focusing because you have nothing in the way like you do with the reflectors. So there's no secondary mirror that is there. So star fields tend to look very nice. Star clusters look very nice. You see, and even splitting double stars and triple stars, I find they pop a lot nicer in a refractor. So, yeah. And there's a whole bunch of terms that come along with these things. You don't need to really worry about this too much, but I mean, some of them are obvious, like doublets being 2 glass elements, triplets being 2 glass elements. You'll see ED a lot, which means that it's extra low dispersion glass. And that's just to reduce some of the other effects that come along from secondary color coming into it. So, yeah, and so as I was saying, one of the big things with a telescope, and when you're looking to, when you're thinking about, and to touch on Alan's point about buying a telescope as a beginner, one of the primary, if you're at the point where you are going to buy a telescope, the aperture is a big deal, right? This is the common, and this is just the usual thing that we do where we make fun of the department store telescopes, kind of thing, right? So one of the things you will see on the department store telescope is, I don't know how many 100 times magnification, right? But the scope itself has an aperture that I could fit my my hand around, kind of thing, right? Now, when you're looking at a telescope, what you really care about is how much, ultimately, there's some other things that you should care about, but really what you care about is how much light can I gather, right? And that's, when we talk about aperture, that's what we mean, right? We're talking about how big is the mirror or the lens, right? Now, in terms of cost, the reflecting telescopes for a big aperture are going to be way cheaper than a refracting telescope. Many people in this club own at least an 8-inch reflecting telescope. They're not that expensive. You can get an 8-inch Dobsonian, and I'll talk about those in a little bit, for $500. An 8-inch refractor, that ain't cheap, right? That would cost quite a bit more. So, and also, yeah. is a very, very serious problem in our club. Many have succumbed to it. Actually, there's a little note here that's good to remember. Moving from a 6-inch to an 8-inch, you get twice as much light gathering capacity. Reason why is because it's a circle, right? So pi r squared, right? So, math. But yeah, you do. So I mean, moving from an 8 to a 10, you get twice as much as well. So there's a massive gain to be had there, right? I talked about focal points when talking about like the focusing on. And this is going to get a little bit technical, but I think it's just worth going over a little bit because you'll see F numbers, and you'll be thinking to yourself, what on earth is that number? So I'll give you a little bit of the background of it, and we'll just kind of gloss over some of the technical details of it. But basically, this number here, right? So this is the focal point, right? This is the point that the light is going to focus on so that you can see it, and then this is the focal length, right? And I'll get into how that works a little bit more. So, yeah. So the focal length is the distance in which the light rays are brought to a focus, right? So that focal point I was talking about. Easy way to think about it is if you have a shorter focal length, you get a larger field of view and smaller magnification. If you have a longer focal length, you get a smaller field of view and larger magnification. Right? So more magnification means if you want to think about it like this, magnification means I'm zooming in on something, right? That's kind of how I have always thought about it. It keeps my brain from getting tripped up going the other way. So the number that you will see bandied about is the focal ratio. There's a lot of there's confusion that comes in from kind of the photography side of things, where photographers will talk about f-stop and that sort of thing. I threw that in here just because I think it's just a funny thing, because I hear the terms as interchangeable a lot. Really, what astronomers are talking about is the focal ratio. I won't talk about any of the photography stuff, but like when we say f ratio, we are saying this is the ratio between the focal length and the aperture, right? So everyone was talking about aperture, how big it is, and then the focal length is how far does it take to focus on that focal point, right? So, and why does this matter? Well, it matters to how the telescope operates and focuses on things. So, and you'll also, this is the other jargon, you will almost more often, you won't hear the term F ratio. You might hear F numbers sometimes. Sometimes you'll hear other F-bombs in the middle of the night, but more often you will hear the speed of the telescope, right? And the reason why they talk about it as speed is really just because of how quickly it focuses it. And there's a slide that comes up that'll explain that a little bit better. But in general, why does this matter? So smaller F numbers will give brighter photographic images and the option to use shorter exposures. That's a really simple explanation for why it matters. So a little bit of simple math. It's arithmetic. So you got a telescope that you've got a focal length of 1,000 millimeters. You have an aperture of 8 inches because I like to mix imperial and metric, because who doesn't? And so what you do is take, so the F ratio of this scope though would be 1,000 divided by 232, 232.2, which is 8 inches because we hate ourselves. And the F ratio of this telescope will be 4.9, and this is how you will see it displayed. So when you see this number, you'll find a telescope that has this number. That's what that means. That's where all that came from, right? So. Fast versus slow. This is the slide I was talking about. I didn't lie to you. So an F8, right, takes a long time to focus on that point. The F4.5 does not take as long. This is just a rough guide to, if you're talking about a fast scope, you mean something less than an F6, and then this is a range of medium, and then a slow telescope would be F12. This is the part where I enter in for dramatic pause and have a sip of water. Okay. Yeah, There's always way too much in this presentation. So, talk about eyepieces a little bit, yeah, I mean, I don't want to turn this into like a purchasing guide. But in general, I don't recommend the sets of eyepieces that you can go out, that tend to be advertised. I mean, they're not bad to have. I especially like them for public observing events because they're relatively inexpensive, and I can swap in and out different eyepieces for what I need that night. But anyway, the thing to understand about eyepieces is they got a number on them, and that number in millimeters, because metric this time, is its focal length. Okay? These will typically range from 3 to 50 millimeters or so. The smaller the eyepiece number, the more magnification you will get. That's basically it. And you'll also lose, and with the smaller the eyepiece, you will also lose something called we call eye relief. So this is really important to the older members because they're I'm going to say they're less patient when it comes to squinting at a telescope. So they like a lot of eye relief. And really, what eye relief is just how when I look at an eyepiece, like can I just hang out here and can I see, from like where my eyeball is, can I make something out, right? And a good eyepiece with a lot of eye relief will give you that ability. So, and I mentioned this before. The magnification again is just so even if you have a smaller focal length eyepiece, you're going to get a lot more magnification, right? And that's just because of this. So just for example, a 25 millimeter eyepiece, which is a common, mid to wide field eyepiece, and a telescope with 1,000 millimeter focal length. I should have used imperial there. 1,000 millimeter focal length will magnify the object 40 times, right? Nice and easy math, actually, right? So that's really where the magnification thing is. And getting back to the department store telescope, I mean, that's the other ironic thing about it, is that you can actually boost the magnification of a telescope very easily by just swapping out the eyepieces. In fact, you can boost it even more by swapping in what we call a Barlow lens. It's a relatively cheap piece of optics that it will very quickly give you a boost in magnification. Most of them are 2 times. There are a few that are you can find 3 times ones, but I don't really think there's much use for those honestly. But having a 2 times Barlow lens is definitely a handy thing to have around. Field of view. I'm going to skip over this actually. Yeah, I'm not going to worry about this. I'm not going to worry about that. Binoculars. I am going to worry about this. So when it comes to binoculars, it actually, I would say, nicely falls into Alan's question about, as a beginner, what should I buy? And what should I not buy? I highly recommend, for a beginner, a pair of binoculars. They're cheap, portable, they're great. You can see a lot with them. They will help you get into hunting down and finding stuff in the night sky. And while I had to breeze through the field of view stuff, one of the things about binoculars is that they will have a wider field of view, which means you can see more of the sky when you're looking through them. This doesn't sound that important, but when you are trying to find something, it's harder to find something when it's highly magnified than when it is less magnified, if that makes sense. So I actually recommend it. I mean, as a starter option, I really recommend binoculars. There's not a heck of a lot to them. They go through here, bounce off these things called what they call horror prisms, which write the object in your field of view. So works really effectively. So I recommend binoculars. I think they're great things to invest in. I'll talk a little bit actually in the announcements. I will talk about binoculars in a way. So spoilers. So binoculars, go get some. You generally want, and generally for astronomy, you want the wide field of view ones. Don't get the high magnification ones. So that's really the only thing to remember there. So like 7x50s, those are pretty good. 10x50s, you know, sort of. Real quick on mounts. So there's different types of mounts out there. They've mostly broken down to equatorial and altazimuth. Equatorial are nice because they control the rotation of the sky. So, you know, the sky, so the Earth is rotating, if you didn't know, and as it's rotating around, it's doing so on an axis, and that actually creates, you know, this, what we call the celestial sphere, and as the sky is rotating, what these mounts do is they actually give you, even if they're not motorized, they actually give the ability to just track along with the object as the Earth rotates, right? So it's kind of set. So it makes it a little trickier for beginners though, because it's a little bit harder to define the objects because your axes are kind of like this, right? And then they have this, right? So it's like I want to go look at something over there, right? And it's like, oh, okay, well I do this, and then I have to do that, and then I have to do that a little bit, and then that, and you have to move things around a little bit. So equatorial mounts can make hunting for things in the sky a little bit more challenging than you might expect. So you might say, oh, hey, there's that object over there, and then you'll spend like a couple minutes trying to figure out how do I orient this thing to get over there. So that is a little bit of a challenge. For beginners, actually the altazimuth mounts are a little bit better because they're a lot more point and shoot, right? So they kind of move like this, and they kind of move like that, right? So, yeah. And one of the best, honestly, I think one of the best altazimuth mounts, and combination of cheap scope, is a Dobsonian. So Dobsonian telescope was invented by a guy named Dobson. And what it is a Newtonian reflector, as we talked about, sitting on a really basic altazimuth mount. What you get here is a ton of light gathering power for very inexpensive. Like I said, an 8-inch Dobsonian runs you about $500. That doesn't include all the fancy other stuff that has, you know, that you probably want to go along with it, like, you know, eyepieces and that sort of thing. But you can have this set up in no time, right? It's like you pull out the mount, you drop it down, maybe set it down nicely. Take the optical tube assembly, which is the reflector piece, set that down. Collimate if you are being good in particular about your observing. Put your eyepiece in, take the caps off, and then you're basically good to go. Like there's it. And what's really great about these is that they're a great way. I think they're an amazing way to learn the night sky because they force you to look around. I learned a good chunk of the night sky just using one of these, you know, and it really helped me out. So I recommend them. So this is usually when people ask me what type of telescope should I buy. I usually tell them don't. I tell them, you know, use your eyeballs. Start with your eyeballs or buy a pair of binoculars. And everybody says, well, but I really want a telescope, right? No one has ever said, when I told them to go and buy binoculars, that no one has ever in the history of me having that conversation has ever said, cool, Brendan, I'll go do that, right? They always say, no, I want a telescope. I really want a telescope. This is the telescope you want, right? Maybe not this big. I wouldn't necessarily recommend jumping right into it. I think this is a 10. But an 8-inch Dobsonian is really good. Okay? So that is my absolute standard recommended telescope. If you can't afford an 8, like $500 is a little bit too much for you. There are smaller ones, and they do get cheaper as you go down. So like a 6 is pretty good too. You can actually see a lot with a 6. I just found I find that the 8-inch, if you can afford it, is really it's the right mix of portability, size, and cost. So, but really the Dobsonian one is a really good pick. I threw in setting circles in here for some reason. I don't know why. I'll skip over that. Yeah, I know, right? Like, who even uses setting circle anymore? I'll talk about RA and DEC at some point. I'll be bored. I'll be excited. Telrads, though. This is a cool thing. I'm going to finish on this. I'm just about done. I don't know why I'm apologizing to you guys for that, because I'm the one running the show, so I'm actually the only person that can actually really stop me. I could keep going for like an hour on this, and no one would actually drag me off. I'm watching Jay. But yeah, Telrads. Telrads are great. These are, so when you go back to here, you got this finder scope on here. most of the ones that come with like an 8-inch dot, like they have those stupid dot finders on them. Those things are terrible. I've never found them to be useful at all. A Telrad is a little bit big for an 8-inch dot, but it helps a ton. And basically what it does, it's used in addition to a finder scope in a lot of ways. So a finder scope is a little telescope that you put on your big telescope to help you find things. And what the Telrad is there's just zero magnification, but it's got this really nice red diagram on it with these circles, right? Fair warning, you will waste a ton of batteries by forgetting that you left this damn thing on overnight. But they're really great. So you just turn on, you point roughly to where you want to go, and then you can use these to figure out where things, to figure out where your telescope is actually pointed to. So highly recommended investment. I think they're really, really useful. So that's everything I had for TMOG. The people that showed up late didn't get that joke. Okay. Thank you. Oh, hello. Brendan again. Still here. Welcome to the Winnipeg RASC. I haven't seen a few of you for a little while. We had an August meeting, but it was unfortunately on the long weekend because that was the only Friday of the month where the Bombers weren't playing a home game. Go bigger. It was a really good meeting last month, and we do actually post our meetings. Abdul has been reporting them diligently for a long time now, and I do recommend going back and watching that one. There's a lot of really good content in there. So I'm probably gonna start sending out those links to a wider distribution of folks. But yeah, I do recommend that. But that was last month. Tonight we got a lot. So you just saw me ramble about all of this stuff for a little over a half hour, and hopefully it was okay. I'm going to be running through some announcements. Then Jay Anderson will be coming up to do his Lost in Space segment, which is his thing where he looks at a spacecraft that's been out there orbiting the solar system, and maybe we haven't heard about it in a little while. So I don't know what he's got planned for tonight, but we'll find out. Then Ryan will give us a what's up. This wasn't a mistake. What's new? Ian unfortunately had to back out fairly last minute, but I pulled together something. So this should technically say me, but I don't think it's going to be that good, so I didn't want my name attached to it. So we'll see. Anyway, and then we'll have a refreshment break, and featuring a bunch of goodies and coffee and mingling. And then we will move into our feature presentation, which will be given by Gord Tulloch, one of our members, and we'll be talking about photometry for amateurs using eye telescopes. We'll learn all about that, what that is. So, I should probably ask, is anybody new? First-timers? Wow, quite a few of you. Awesome, welcome. Welcome to the meeting. It's great to see you. If you have any questions, feel free to come talk to me during the refreshment break. There are also some council members in the crowd, and I recommend talking to them too if you can find them. Actually, in general, you can just talk to anybody, and they'll probably be full of information and goodwill. So, welcome. Okay, so into the announcements. The weekend before the Sprucewood Star Party, we were out in Riding Mountain National Park. We had myself, Brian was out there, Kathy and Kevin Davis, and then one of our Brandon members, Trevor, came out as well. So I got into this when the park reached out and they wanted us to do an observing night, and I was like, okay, yeah, we can probably do that. They offered to pay for camping and that sort of, and said that they'd offered to put up, to donate some money to the club, which was cool. So I was like, okay, that's cool. We can do that. And then what they did was they actually put together an entire weekend full of astronomy-related activities. So they had, on Friday nights, Trevor and I did kind of an ad hoc observing event for about 100 people, showed them Saturn, They turned the lights out in the park area, which was really cool. So I got to do I did a bit of a sky tour and showed some people some deep sky objects, so that was really neat. On Saturday, we did some daytime stuff, and then there was yoga at dark, which apparently had like, I don't know, like 100 people or something like that. It was pretty wild. And then there was an indigenous sky tour, which we got to go. They let us attend this for free, and it was really good. It was a really good take on the night sky, and yeah, I got a lot out of it. It was really enjoyable. And then Sunday night they had this. We did more of the daytime stuff, and then Omnic After Dark is a thing we'll talk about in a little bit. And then we had another free viewing event that I think Kathy and Kevin may still be recovering from. So we'll get there. So during the day, and this is one thing that I was really blown away by, was we had an immense amount of support from the park. It was really great. They had all this stuff set up. The park interpreters were building these. I don't remember what the heck these things are called, but you know, like I don't know if kids I guess still do this, where you fold these pieces together and you know they fold out like this, you know, kind of thing, right? You pick things. Anyway, yeah, kind of origami, but there's things inside of them, right? And there are little flaps that you fold up, you know. So when you move to like a specific square, you fold it up. Anyway, but they had little star facts and like space facts and astronomy stuff in there, and it actually folded out into a little planisphere, which was neat. So anyway, so we did a bunch of outreach. We had magazines to give away and rocks to hold all of our stuff down from the wind, moon maps and that sort of thing. So it was a really good weekend. We had. Despite like there were some clouds, so we did get to look at the sun, but we had a lot of people out and had a really good time with it. I got to go out and do a little bit of sky touring. We actually met. I don't know if James is here tonight. Hey, hi James. So we met James out at the Indigenous Sky Tour, and while we were there, I actually did a little bit of semi-illegal green laser pointing, because you can see the planes. But yeah, this is me doing it. I was helping out a little bit, just showing some objects in the night sky, and James got a really good shot, and I thought that was cool. So that was our Saturday night, and then Sunday night we did our public event. The public event was basically Brian, Kevin, and Kathy with 5 telescopes. And then we had a couple people from the park helping out. The number that I got from the park was close to 300 people. That's a lot for 3 people to handle. So like kudos, like seriously, like you guys handled that very well. But there were immense crowds. It went over great. Everyone loved it. So good. Yeah, it was really good for us. Had a lot of fun there. Now you might be asking, well, Brendan, where the heck were you? I was not off drinking beer. Well, I could have, but I wasn't. I was doing this weird thing that they put together, where they had groups of 10 come through, and they did a walk through this marsh trail. And because it was groups of 10, they said, they asked me, like, what do you want to try and do? And I thought it would be really neat to try to do a binocular tour for non-astronomers. So I managed to wrangle together about 8 pairs of binoculars, and as people came up to the station, I handed out the binoculars, and I showed them stuff with the binoculars, using a green laser pointer, and they loved it. It was actually, so despite the fact that I was telling you that, like I've told people to go out and buy binoculars when they asked me what kind of telescope should I buy, people actually walked away from this wanting to buy binoculars. They were really impressed at what you could see with them. It was really, I was absolutely amazed at how well it went. The best experience that I had was, I had a couple kids come up. They were probably age 10 to 12 or so. And, so they said, hey, we want to look. And I was like, yeah, sure, absolutely. So I handed the binoculars, which are comically, they're the big ones, right? So they're kind of like comically sized for them. It's like, hey, you got them? Okay, yeah, no, we got them, kind of thing, right? And they took the binoculars, and I said, okay, I used my green laser pointer looking like a wizard, right? And I was like, pointing towards the Milky Way, and I just said, if you look up through here, you will see thousands and thousands of stars. And so they took the binoculars and they followed my green laser pointer and they looked and they were like, oh wow, I get that "oh wow" a lot, right? Not because of me, but because I'm usually at a telescope, and I'm showing kids stuff through a telescope, and the reaction is, "oh wow," right? Because they're looking at Saturn, they're looking at the moon, or the Andromeda Galaxy, and it's cool. It's really cool. What was different about this experience, and what made it really impressive for me was, once I showed them that, they were off and running. I didn't do anything. I just sat, like, they took those binoculars and they just started looking around, and they were like, "oh wow, what's that?" kind of thing, right? And they started like panning around all over the place and looking at stuff, and they're like, "why is it like there seems to be like there's like this little thing over here?" And I'm like, "oh yeah, that's a star cluster. That's a little grouping. That's a little packet of stars." They were basically just letting their own curiosity guide their views, which was something I never get at these public events where I'm just showing people objects through a telescope. It was really rewarding, and I don't know, it's neat. I want to do it again. I want to try incorporating I want to try incorporating that kind of hands-on thing into more of the kind of public outreach that we do. So anyway, it was a really good thing. I don't know if anybody here remembers or knows Buzz Crowston. But he was helping out with the naked eye stuff, and then Trevor was over doing a telescope observations. People have a little more intimate, hands-on time with a telescope, which is kind of neat too. They also threw out space-themed food and mocktails, so that was kind of neat. That's the march. So it has, it was a little scary because I'm like, do I really want to have all these binoculars out there? But it was fun. So, and if you're wondering, the telescope was actually on a different platform, so it wasn't shaky and all that kind of stuff. It was a really good event. The only downside is we did start a little bit too early, and we were fighting with some clouds, but despite all that, it went great. So that was my little writing mountain tour. Hopefully we do. I'm hoping we do it again. I was going to mention too. They also donated. They donated $700 to the club. So that's money that will just go right back into our society. So that's cool. Yeah. Anyway, speaking of money, we have calendars for sale. I forget what we sell these for. I think it's $12, $1 a month or something like that. Stan, I don't think is here yet, but he has calendars. So if you want calendars, you can buy them off Stan when he gets here. These are really nice. They make great gifts, etc. Recommend picking one up. One of our members has released a book. It's Meteorite Hunting and Collecting: The Enthusiast Guide by Ralph A. Cronin. I got mine signed. There was a book release party at Spruce Woods. He knew my name. But yeah, I haven't actually had a chance to read it yet. But Ralph knows meteorite hunting and collecting. He knows a lot about it, and I'm just leafing through it. I think it's a really good amalgamation of a lot of information that's spread around. So I recommend checking it out. The U of M open houses are still running. They continue to be held at University College, room 240. Danielle's been running these. I haven't been able to make it out to one, but from what I've heard, they're going really well. But it's a clear night. She's very happy to have some RASC folks out to help with telescopes, maybe. So yeah, if you want to get yourself involved with these, feel free to reach out to her. She's been changing up the topic every month, so for this month it'll be solar system formation. So that's neat. Other stuff, Okemic Martianite. These are picking up again now that the sun is setting at a reasonable hour. Astronomy time. The next one's on Thursday, September 20th. They are, I forget the guy's name now, I should have written it down. But the one coming up at the end of the month will feature somebody who goes by the Night Sky Guy. I think his last name was Fazekas, and I don't remember anything else about him. I should probably know him, but I don't. But it sounds like it'll be a good one. So I recommend checking it out. If you show up with the telescopes, they will waive the $10 entry fee. You should bring your RASC membership card as well, just to show that you are a RASC member with a telescope. So, and you have to take the telescope out and actually do some doing with it. That's kind of the deal. So don't tell them that Brendan said if I show up with a telescope and do it. Okay. Speaking of telescopes, because that's a lot of what we talk about. If you are a club member, you get access to our loaner scope program. So we have a couple telescopes that you can take out, and yeah, they go for 1 month at a time. This is our selection right now. Two 8-inch Dobsonians. That other Brendan guy was talking about these, wasn't he? But yeah, so we got 2 of these, and you can take them out for a month. They're really good. We also have a PST. This is actually in my possession currently. I'm going to be using it at school on Wednesday, but after that, I'd be happy to loan it out to whoever wants. So you can just come talk to me if you're curious, and we'll work it out. If you're a member, you get access to the Glenlee Observatory. This has a whole bunch of stuff that is quite useful, like a warm room, which is really handy in the wintertime. We have a 12-inch scope and a 14-inch Dob out there that you can use. It is close to the city, so you are kind of dealing with the sky below. But I've seen people do some really good photography work from Glenlee. It's a bit more of a challenge, but it's closer to the city. And when it comes to planetary stuff, as the planets continue to remain out, if you want to go meet up with some other RASC members, it's a good place to congregate. We also have the Explore the Universe program. It's a good way to get yourself into astronomy, or to re-familiarize yourself with a lot of the common objects that are out there. There is a list of objects that you can go and try to find that are right here. So we usually pick a few every month and say these are the ones that you should go and have a look at. I recommend doing this. I think it's really good. Something else I was going to say. Oh yeah, you will actually, so the way this program works is you record all of your observations, and this is, if you go here, this will have all that information with, less of the factual layers I'll probably give you. But if you go out and do this program, you will record all these things that you observe, and you'll submit that to the RASC, and the RASC will acknowledge that and send you a certificate. And won't that make you feel great? Okay, speaking of feeling great, I'm going to stop talking for a bit now, because I've been going for a while. And I'm going to let Jay take over, because he is going to do Lost in Space.
Well, those of you who've been here before know that Lost in Space is about those astronomical satellites that we never hear about. Now, everybody knows about the Hubble Space Telescope and maybe Chandra and a few others, but what we're going to do is find the Lost in Space one. And the one I'm talking about tonight is called NuSTAR. Now, NuSTAR stands for Nuclear Spectroscopic Telescope Array. It tells you just about everything that it does. It likes to look at the nucleus of galaxies and things like that. It has a spectroscope on it which will break the light that it's looking at into various wavelengths. What it doesn't tell you is that it's actually an X-ray telescope, and it's an unusual one. Also unusual was its launch, which was dropped from an L-1011 in this Pegasus rocket and then put into orbit. And once it was in orbit, it stretched itself out into a rather curious shape. I got to stand away from the speaker to avoid the feedback. So what we have on it is a kind of a long boom that extended after it was launched. Solar panels on this side, and the whole thing is a telescope. The detectors are down here in the control system for the satellite, And these are the optics. And it's the kind of optics that you'll never see anywhere except in an X-ray telescope. You can't just put a mirror up to look at X-rays, because the X-rays will do one of two things. They'll go through the mirror, or they'll be absorbed into the mirror and they won't reflect anywhere. So what we use is called grazing incidence reflection. And you know, if you look at some kind of a light source, like the sun setting way down low, and it's the surface of a lake or something is in the way, that the light will skim just off of the edge of that. Or if you have a sort of partially polished surface and you look at something, if the light is right on the edge of it, you can see a reflection. And that's what happens here. The incoming X-rays graze this surface and are bent, and then they graze a second surface and are bent into a focal point. It takes two of these surfaces, one paraboloid and the other hyperboloid. Now, this is the sensor, one of those two sensors here. The first surface is in this module here, and the second one is in this module. And each one of these, you can barely see it here, there's 133 rings of these built up. We're only showing 4 here, but there's 133 of them in there, built into this kind of honeycomb all the way to the center. And each one of them is actually one of these strips. Those 133 times the number of strips. So actually 9,000 of these little mirror segments in these things. They have to be very, very precisely made, and they have to be very precisely aligned in order to get them to divert X-rays into a focal point. The thing about new stars, it detects very high energy X-rays. There's lots of X-ray satellites out there, but none of them reach the high levels of energy that this one does. So they're looking at the most energetic processes in the galaxy, in the universe, when you start observing with this instrument. It also has detectors that detect X-rays coming in from the sides, so to make sure that the detectors that are sitting down here are actually collecting X-ray photons that are coming from the target. If they have a simultaneous detection from the side, that they get a detection from one coming in, or what appears to be coming in from the front, then they will eliminate it, because that just means the detector was triggered by an X-ray coming from somewhere off to the side. One of the, it's looked at many, many instruments. It's a very valuable satellite, even though you don't hear much about it, because of its capability to look at this high energy. So one of the things that looked at is Cassiopeia A, which a lot of us are familiar by name. This is a visible light photograph of it, and it's actually quite a faint object, but it is a supernova remnant that went off in 1667. At least that's what we've calculated. Didn't go off in 1667, that's when the light got here. It was a sort of vague observation of a star at that time that somebody might have seen it, but we believe there's too much dust around this to have actually seen the supernova explosion, even though it's relatively close to the Earth. So with the hard X-rays, though, it's pretty easy to see this, and in radio waves as well. And what they looked at when they examined it, and here's an image that combines information from the new star X-ray spectrum plus the Chandra, which detects lower energy X-rays. So here's a combination. This is titanium, which is emitting in the hard X-rays, is what we call high energy X-rays. And then we see emission from iron over here and from silicon and magnesium in what seems to be a jet out here. Now most supernova, when they go off, are believed to form a jet that fires out material in opposite directions. That seems to be what we're looking at on this one. The interesting thing is you sort of think of a supernova explosion as blowing everything out to the sides equally. And from images like this, we see that they don't. In fact, most of the titanium is coming out in this direction on this side, the iron, and preferentially here and some here. So it seems to be symmetrical on each side of this explosion. And the jet is certainly one-sided, although it may be that there is another jet here that's coming out on this side that's not visible. So when you put all of this sort of thing together, you have to go into a model and say, well, okay, all my models have said that supernovas explode equally in all directions. Now you have to figure out why they don't do it. And that is a challenge for the guys that know the mathematical equations. So New Star, in a way, is, well, it will give you these spectacular pictures of these cores of active galaxies and supernova remnants and things like that. Is really a satellite that's adding in to the information that we're getting at lower energies from other satellites. Here's a study of Eta Carina, which is not visible to us. It's this patch of bright stuff in the southern sky. Eta Carina is an extremely unusual stellar object. It's actually 2 stars, one about 30 and 90 times the mass of our sun in a very tight orbit. And the massive star, the big one, has a slow solar wind that's blowing material off of it. It blows off about 5 Earth masses every decade or something like that. And inside that envelope of material that's being blown off is this compact star with 30 masses of the sun, which has got a very, very high speed. It's a very hot star, so its stellar wind is very high speed. And of course, it blows holes in the emission from the bigger star. So what they're actually seeing in it is a sort of spiral track as this one star in its 5.5-day orbit creates these spirals in the larger emission. Well, you can appreciate with 2 huge stars like that, with all of the energy they're outputting, the places where these 2 emissions from each one come together forms a shock front. And that shock front, extremely high temperature, breaks everything up into electrons and atomic nuclei, which are then energized by the magnetic fields that are contained and so on and so forth. It's one of the highest energy regions in our galaxy. At one time, Eta Carina was the second brightest star in the sky, since faded away from an eruption in the 1880s. Now, sorry, I said 5.5-day, 5.5-year orbit on these things. When you look at Eta Carina, now here they haven't drawn a picture of what New Star is seeing, but contours of energy is seen. And those contours of X-ray energy are superimposed on an image taken of lower energy X-rays by Chandra. And so what we're seeing in these is that there's a lot of energy, a lot of emission that wasn't seen by Chandra centered on this binary system. And this X-ray energy is capable of accelerating particles to tremendous velocities as a result of its interaction with the material being thrown off by these 2 stars and with the shock fronts that they get. And so one of the things we discovered about it is that it's a source of cosmic rays, which are particles like electrons and hydrogen nuclei that are moving nearly the speed of light, and of course they're striking the Earth all the time from innumerable sources in the universe. But it's always been a bit of a mystery about where they all come from, and when you start seeing how much energy is involved in a stellar pair such as Eta Carina, here's a Hubble picture of what it looks like in several wavelengths here. Very unusual object. But anyway, when you start seeing what kind of energies are involved in this core here, outlined in green, plus the lower energies in the colors, you realize that the processes are more than capable to accelerate particles to the speed of light, or almost to the speed of light, and then throw them out across the galaxy until they get to us. A lot of this is complicated. It's not only the X-rays that are doing it, it's the shock fronts in between the 2 stellar winds from these 2 stars. It'll be very interesting to get really high-resolution images of it, but it's not one of those places where you'd ever want to go close to with the amount of X-ray radiation and gamma radiation coming out of it. Another interesting object looked at by New Star is this strange numbered thing here. It's a pulsar. Pulsar is an extremely rapidly rotating neutron star. This pulsar has an enormous magnetic field on it, 15 trillion times stronger than the Earth's magnetic field. And 20 kilometers in diameter, so it's a star that's been squashed down to 20 kilometers. It's not quite made it to a black hole, spinning at 7 times a second. And so once again, what we have is an extremely strong magnetic field that's whirling around at an enormous speed. And if you know anything about engineering, you throw a couple of ions or charged particles into that, and you basically have a giant electrical generator. And so again, we look at a combination of images from Chandra, which are the reds and greens, and from New Star, which is this. We get a lot of structure that we now have to determine what causes each one of it. So this is a nebula up in here that's being, essentially the emission from the pulsar is running into the nebula and causing it to be illuminated, probably particles that are flowing into it. And this nebula is associated with the pulsar itself. So because you're moving so quickly and generating these high-speed particles in here, you're crashing into just about everything. But one thing about high-energy observations is they reveal what's going on in the core. If we look at a sort of typical example of a pulsar here, we have the 20-kilometer object in here. We have a lot of dust and gas in orbit around it, which is glowing. And we have a jet coming out of one side, and right in at the bottom of the jet is a region they call a corona. You know, and a corona is one of those names like when you go to the doctor and instead you've got eczema. Well, eczema is a name that means you've got a skin disease, I don't know what it is. And a corona is that way, got a bright point, but I don't really know what it is. So we give it a name, but we don't know why it's there. But what we're seeing in the New Star observations is the emission from this extremely bright point, which seems to be where the acceleration takes place that blasts particles down this jet, confined in the jet by the magnetic field, among other things. And one of the ways of looking at this data is to plot it on a graph. So this is like a spectrum. This is the energy of various X-rays, and this is how many of them there are. And these white dots are the observations that New Star sees across this energy. And right now, they've modeled according to 2 ways. Because this is an extremely strong gravitational field, and this corona is very, very close to the neutron star, it's subject to extremely strong gravitational forces, which give it a number of relativistic effects. And so one of them is that it tends to smear out what would be the sort of steady state observation. The light waves at one point are smeared out by the rotation of the neutron star at 7 times per second. And plus the light or the X-rays that are coming out of this intense gravitational field are actually slowed down and converted to lower energy X-rays as they leave the gravitational field. So what we see here is, this is what it would be, they think the emission would look like if it were not affected by these gravitational fields. And this is what they actually saw, and this is a calculation in orange here of the way the mathematicians came up with what the emission looks like after it's blurred by the gravitational effects and the rotational effects. What we see here is what's called a P Cygni profile here, which is characteristic of many variable stars, not just neutron stars, and it's a sign of the intense rotation in the star itself. In this also, when we look at the emission in the various wavelengths where we can detect which ones are from various elements, this is primarily iron emission in here, and this is primarily iron absorption. The absorption comes in the gas cloud from the iron molecules or iron atoms that are highly ionized that are absorbing the light in here, and the emission comes from that outflowing wind in the jet. So we not only see signs of the rotation, but we also see signs of the various parts of this corona as a result of being able to look at things in these very high energy X-rays. And so it would appear that things are going on in this environment. Whether this is an unusual neutron star or a typical one would only be solved by going and looking at a lot more of them. But you can see here that just before it went into these observations, the corona around the black hole suddenly increased in brightness and moved inward toward the neutron star and another hole. We don't know why that happened. And it seems to be continuing up to at least the point where I had information on this one I'm putting together. So it's a mysterious object, but at least new stars helped us interpret some of the things that are happening really close where all of the energy is being deposited. And so, now when you keep an eye out on it, usually with Chandra stuff, you might see in the pictures, you'll often see there's some new star data that's put in there with it. NASA has a little app. NASA has an app you can run on your cell phone or your iPhone. Put your own face in one of these things. The hard part was getting the app to hold it still.
I also like how you made fun of my TMOG acronym, but new stars apparently okay. Okay, and we will now move on to What's Up with Brian.
Good evening. So, maybe someday we'll get like a really nice clear skies. Maybe, you know, it's not the smoke, it's clouds. Okay, I'm going to talk briefly about what's on September. Oh, I missed it. We'll start off with the planets. I got some shocking news. I really like Mars, so unfortunately Mars is going to drop its magnitude in half by this month. So the only really planets you can really observe would be Mars and Saturn, maybe a little bit of Jupiter, but that's about it. So that's all I have to say for both planets. Well, I have a little bit, I'll touch a little bit about Mars, because it reached its peak on July the 31st, when it's like 24 arcs across. Now we're already in September. I was hoping maybe someone convinced me that, well, we still have August to look at it. And of course that turned out really nice with all the smoke. So that kind of like depressed me a little bit about Mars for viewing. I tried, September, but too many events during that day. Even that Sunday that we have, Mars wasn't that great. But so my point is, Mars is quickly fading, it's picking up speed, and maybe, just maybe, we can still catch some of it before it gets too far away. All right, just a little chart here about why I'm stressed about Mars. So 2018, this year, it's going to be 24 arcs across. 2 years from now, it's going to drop only a couple arcs to 22. So maybe in a couple of years, you know, we might be able to see something then. So, you know, it's now, maybe in a couple of years, we'll have Mars again, but we'll see how it's going to turn out. Maybe more smoke. All right.
Or dust storms.
Yeah, just yeah, that was another good one too when I hosted that Mars event. Yeah. It's calling it Desert Storm for some reason. Anyways, just kind of give you an idea what the planets are in relation to us. Okay, you can see how Jupiter is kind of like setting quite early during the day. We've got Saturn. Mars is, like I said, relatively close to us, but I don't really observe it. Hopefully the next couple of weeks we'll see exactly what's going on with Mars. So this is today, right now. almost right to the minute, maybe. Pretty close. Okay, so like I said, we've got Jupiter, we have Saturn over here, we have Mars. So I think around 10:30 at night, Mars would be due south. So again, hopefully we'll get some clear skies. I was going to host a members' night tomorrow night, but I just checked the forecast on both accounts, clear sky and Weather Network, and it doesn't look too promising tomorrow, so I guess we won't have a members' night tomorrow night. Anyways, okay, so what's happening in September? Well, not much. We do have the zodiacal lights, which is actually kind of happening very early in this month. And when I checked my notes last year, it was more in the latter half of September, but now it's in the earlier half of it. So we've got 2 weeks, so I'll explain more about that later. What else? Well, we have the equinox on the 23rd, and the new moon is, just a few days ago. So, and of course, it's been raining all week, it's been raining all weekend, so Winnipeg, what can I say? I want to bring this up because we kind of touched about it a little bit. We're at that Riding Mountain Park event, because there's one guy that kind of mentioned about a meteor shower. I don't think I have it listed here. I think he mentioned another one, but I did say to Brendan, probably the most ones where it's like only 2, maybe 5 per hour. But during this month and a little bit of October, we do have lots of smaller ones. Not that big. There's more, trust me, there's more meteor showers, but I can't list them all. Because there's like 1 or 2 an hour. But the point is, they're overlapping a little bit. So now until October, you might get a chance to see a meteor. Hopefully. If we ever get clear skies. I'm going to just talk about that all night. Okay. Hey, I did come across, I do remember from the beginning of the year, I talked about, there's 2 comets this year. Comet 41P, there's another one in December the 3rd. Magnitude's going to be around 3 or 4, but this one's only a magnitude of 7. I haven't observed it yet again because of clear skies, but some people were able to see it with a magnitude of about 3 around Mexico or something like that, but I haven't observed it, so I really can't tell you. So it's right about here, so you got Gemini here, and Urigal here, and every website that I went to try to get a pinpoint of where it is, it's right about here. Some people say it's here, some people say there. Okay, so it's right about here. So close to I can't believe someone says, oh, it's in the constellation Gemini. No, it's not. It's more closer to here, to Urigal. So anyways, I have yet to see it, but hopefully it started rising about 10:30. I was hoping to have the members' night tomorrow night, and I hope to God I was going to have a look at it and photograph it, but I have it pegged around 3:30 where it gets pretty high enough to maybe see something. It's supposed to be a naked eye, but we'll have to wait and see. Okay, zodiacal lights. There's a lot of information here, but it just kind of gives you an idea of what it is. We do have some new members here. Chances are you probably haven't seen it, but I do have some pictures. Basically, the geometry has to be right. I did mention that in one book it said it's like leftover creation from the solar system, the dust. So if the angle is just right in relation to the sun hitting it, right, we get the nice little soft pyramid. Happens in the spring and fall only, because that's when the geometry is just right. So I'll talk a little bit more about, okay, so I have it listed here, it's 5 to 19, so the next time is 29 to October 23rd. Oh, I think that's wrong. I didn't change that. So ignore that, that's right. Sorry. This is wrong. Okay, so I've seen it myself, thanks to Jay when we were at Arizona a couple years ago. So I seen it the first time, I still remember to this day, it's quite spectacular. It took me a bit of while to pinpoint it because I was expecting something really big, something really small, it's kind of hard. But you have to get a dark site. Unfortunately, it's in more towards the morning part of it, not the evening, so either you stay up or get up early just before the sun rise, and hopefully you do see it. Okay, this is a picture of it. That's Jay there doing his stuff here. So this is the kind of part of it right here, just right here. So kind of give you an idea of what it's supposed to look like. This is, I think, it's a little bit better picture, what it's supposed to look like. It's a soft pyramid, This is probably more like a 30-second exposure, but again, it's quite nice. Not everyone gets to see it. I'm shocked because apparently even the more professional astronomers have not yet, they haven't seen it. So don't worry if you haven't seen it, but maybe, I think in the springtime when I do a members night, maybe I'll point it out then if we ever get a clear sky or smoke. All right, so that's all I have to say for what's up. Thanks.
Okay, thanks, Brian. I'm just going to leave that spin there for a minute. Actually, on the note of that comment, Jay, during the 2 hours and 37 minutes of clear skies that they had out of Spruce Woods, he did manage to photograph it. It is quite nice. It's got a good little tail to it. So, like Brian said, if it clears up, you can go hunting for an Auriga. Pair of binoculars. Pair of binoculars. You would be able to see with binoculars. I'm just going to keep saying binoculars all night. Yeah, that's nice. So I got a really good recommendation for you. It's an 8-inch Dob. You can also see icon with an 8-inch Dob. Okay. So as I was saying, Ian regrettably had to back out. I, being a prepared presenter, naturally had this presentation ready to go in my back pocket at about 5:30 tonight when I made it. So this will be brief, but heck, we've been running along here for a little bit, so I'm sure you're all happy to hear that. So I'll run through a few news items that I scoured from my inbox. It's funny, because I had to slap this together, I was looking for like the best resource that I could find. And that might actually be the most important thing that I can tell you tonight, is if you are stuck in a similar position and you have to throw together a what's new presentation, Universe Today's email digest is a really good resource. I signed up for their email, and they send you an email once a week. And it's just a bunch of interesting astronomy and space science news stories. So Universe Today, really good. It's a good aggregator of this kind of stuff. Anyway, so item 1, on the origin of Steve. So I think by now most of us have heard of Steve. It was suspected to be this, it's been this thing that's been observed by aurora hunters for a long time. It's been photographed heavily by a lot of people in the club. We actually had Alan Dyer out back in the springtime at the planetarium giving a pretty lengthy talk on this. So. But at the time, there was still some contention about what Steve actually was, because there were some people were suspecting, oh, it's just a type of aurora. But the question kind of remained, there was no evidence that it was actually aurora. So the question was, well, is it or isn't it, right? If it is, it's still interesting, But if it isn't, then it's even kind of weirder, right? So what this team did, that I regrettably don't mention here anymore, but this team of scientists, what they did was they went and took data from the Polar Orbiting Environmental Satellite 17, POSE-17, to measure the precipitation of charged particles in the ionosphere during a STEAM event. Also, really, for like a night of acronyms, like Steve has got to be one of the worst ones. They actually acronymed it into something that I won't even tell you. But we can talk about the name of it. Ask me about the name of it later at the refreshment break, or Boston Pizza, or whatever. Anyway, but what they were trying to do here was they said, okay, we have a satellite that can actually observe for charged particles. So we'll just wait for Steve to show up, right? And we will use, and then what we'll do is we'll look back at the data from that satellite, if it was looking at that area, that area of the Earth, and see if we see any charged particles. No charged particles. All right. So what this means is that it's probably not aurora. It's some kind of sky glow. They don't actually know what. So the mystery of Steve remains. the project scientist, or the team lead, said that our main conclusion is that Steve is not an aurora. So right now we know very little about it, and that's the cool thing, because this has been known by photographers for decades, but for the scientists it's completely unknown. So the mystery continues. Item 2, water ice. Been on the moon's poles. So these spots here aren't ice, despite the fact that they are conveniently colored blue. What they are, these are the shadowed regions of craters on the, I can't remember, I think this is the South Pole. The South Pole of the moon where light never actually hits. So they are permanently shadowed, right? So this is, yeah, this is, yeah, this would be the north. This would be the North Pole. There's another image like this to the South Pole as well, but this is the North Pole. And so what we're looking at here is a collection of data put together by a variety of instruments. And where you see these green dots, and not excluding my laser, of course, is where you see is where we actually have detected water ice. So the big difference here, and so I think a lot of people are going to be like, well, yeah, of course, we've been hearing about water on the moon for a long time. But what this was really, so what the previous data had been more indirect evidence. There hadn't been anything entirely concrete. So it was like, detecting, so there was a little lander that they shot in and they detected some hydrogen outgassing and that sort of thing, right? So using some spectroscopy, they're able to detect some of those, some elements that would indicate water, right? But no actual confirmation of water, right? So what this team did was they went back and actually looked at a bunch of different instruments from a couple of different spacecraft, which is really cool. Like there's a whole whack of acronyms up here. Whack of acronyms, that's pretty good. There's a whack of acronyms up here, and they, So, and what those are, there's a bunch of spacecraft up there, and similar to like what Jay was talking about with Chandra and New Star, right? Is that you have these different instruments out there, and you can actually you collect a lot of that data, and some things are better looking at other things than other things, right? Everything has its own little specialization. So what this team did was they took all this data and put it together into a pretty good collection, and they were able to, and what they found was. They looked at this data and they found absorption features that were similar to those of pure water ice that had been measured in the laboratory, which was really, really direct, really good sign of water ice. So, it's good. Yeah, what's interesting too is that the water ice itself has a different distribution than Mercury and Ceres. So on Mercury and Ceres, it's relatively pure and abundant, and so, but on the moon, it's kind of patchy. And what this indicates, so the spectral features of, because I totally was prepared for this, slow condensation from a vapor phase, either due to impact or water migration from space. Cool. Just interesting. Moving on. Item number 3, these Parker Solar Probe. I could stand up here and talk about how cool this probe is. Or how hard it is to get a probe to the sun, or how this thing is going to fly through the corona, and it's going to help revolutionize our impression of, and understanding of the corona and the solar wind, and solve a whole bunch of mysteries. But instead, I'm just going to show you really cool space launch pictures. Pretty. It gets better. Look at that. Yeah. Like, this is good. Like, this is, I saw these pictures and my mind was blown. I was like, this is incredible. I have no idea how that camera didn't melt. It's just, it's so good. Look at that. It's incredible. Like, that's nuts. I can see that. Incredible. Look at this. This is just, I don't know. I think it's absolutely amazing. Anyway, yeah, so, the guy who took those, his name's Glenn Davis. Glenn Davis Photography, if you want to look at some higher res images of those. And this is what happens when you're short on This is the last. This is the last one. I thought this was neat. So, briefly, the Oort cloud is a thing that we suspect exists orbiting our solar system, like enveloping our solar system, right? And it is just a bunch of debris out here, right? So this is us, right? And this is a logarithmic scale moving out in terms of distance. You know, so these are all the planets, and then there's Pluto, and then we get to the Kuiper Belt, where kind of Pluto starts here, right? And then more of the Kuiper Belt is out here, and then there's a heliopause, and yada yada yada. The Voyager spacecraft should be out here on somewhere around there. So the Oort cloud, which is like super far out, we believe that it exists, but we can't detect it. And one of the challenges is that because we're like similar to what Brian was saying about the zodiacal light, the thing with the zodiacal light is that it's kind of diffuse, right? And we're kind of close to it, which makes it hard to observe unless you have the right conditions, right? And the Oort cloud is even harder because it's so distant, so you don't even get any light bouncing off of it, right? It's just kind of this diffuse leftover material, right? That's just orbiting, enveloping our solar system. Now, so there was a paper that posited that we could potentially detect Oort clouds orbiting other stars if we were to look in very small wavelength observations. And fascinatingly, they felt that the CMB surveys, so cosmic microwave background surveys, were a really good way to do this. So, just for instance, so these are whole sky maps in the wavelengths that they would be looking at for these things, and by this telescope called Planck. And so these were basically the whole point of this data was really to look back and you know, see the coolest, like not as in, you know, awesome, but like chilliest, you know, region, you know, seeing space in that temperature, right? And using all of that information to do things like understand the origin of the universe and the creation of the universe and, you know, the Big Bang and all that kind of stuff, right? But what this team did was they said, no, screw all that. We could use this to maybe find these Oort clouds orbiting other solar systems. And so they took a shot at this. And so far, and this was like really, really early, but they've actually been able to, like, they have some good candidates that look promising. And so now what the next steps are is that they're going to be taking the Gaia data, which is another spacecraft that's out there that has really done an amazing job of mapping things, and using all that data and some other data to try and see if they can get a positive detection. So it's a thing that's still in the works, but I thought it was a really neat approach to trying to find stuff around other stars. So that was everything I had. It is currently 8:30, and I think it's time for a refreshment break. So there are cookies and stuff. Cookies and stuff. There's coffee outside and other drinks. And we will meet back up at 9 o'clock. The second announcement is that I was wrong. They're not $12. They've gone up by a significant percentage, actually. They're now 13. I know. Still worth it, though. Still worth it. So, $13. Yeah, worth it. Totally worth it. No, I'm jokingly being sarcastic. They're great calendars. Anyway, yeah. So if you want calendars, you can give Stan some money and he will give you a calendar. Anyway. So I think it was back in the spring, our presenter, Gord, had put together an article for our newsletter, Winnicentrics, which you get if you're a member. And it was a really good article on using eye telescopes, which he'll explain to you what they all are. But it's a network around the Earth of telescopes, and doing a bunch of really cool astronomy with them. And I think it's a really neat opportunity to be able to do some astronomy if you're one of the types that is like I got work in the morning, or, like, it's really cold out, or, there's mosquitoes, or, it's cloudy, or there's a giant forest fire that's causing smoke everywhere.
Or all of the above.
Or all of the above at the same time, right? So I was really happy to see that article, and I was like, hey, Gord, you want to, maybe, turn this into a future presentation? And he said, yeah. So that's how we arrived here tonight. So, Gord, take it away, please.
Thank you. Can you hear me okay? I don't need the mic, do I? What? Good? All right.
No microphone.
No microphone? No.
Yes,
No
microphone.
comment.
You need the microphone.
No comment microphone. All right. For the broadcast.
Oh, yeah, also, yeah, it'll help with the...
Oh, right. Okay.
How's that? I can use my FM voice. Well, hi there. I used to do this a lot. As a matter of fact, I was joking. Where do I stand? Okay. I was joking that it used to be the only way they could get me to come to meetings is make me present. So, it's been about 8 years since I was last really active with the club. Kids happen, right, and stuff. So just a bit of an update, and I'll tell you what I've been up to. So, and hopefully this works. And hopefully I'm pushing the right button. There, okay, so that's me. I've been a member of the RASC for longer than Brenda's been alive, and I think that the first meeting I went to, I wanted to come and talk to somebody about getting some software for my Apple II computer to convert RA and DEC to LPAS for my dog Sonia. So
I read about those in history class.
Get off my line.
Right after the paleontology lecture, you got that one, right? So I've been around a long time. More recently, I've become a member of the American Association of Variable Star Observers, and I really like the code they gave me, Tiger. So that's the only cat content you're going to get. Dale, sorry. But yeah, that's my VSO moniker, and you'll see what that's all about. So what I do these days is something called photometry, and that's incredibly boring. So I'll try to make it interesting for you. What's exciting about photometry is not the doing of photometry, it's what it tells you about things, and that's pretty interesting. So we'll try to keep it interesting. What have I been doing for 8 years? Kids, I have 2 teenage boys, very active. One of them likes to shoot things. He likes to shoot guns, and he shoots about a 295 in archery on a 300. He's an instructor in archery range and all that kind of stuff. So the other one likes to get shot at. He's a national level lacrosse goalie, and we spend a lot of time in stinky lacrosse arenas. And oops. And I'll figure out the buttons eventually. He's been a national champion. Manitoba's done very well at the nationals in lacrosse. We nearly beat BC this year, which is a little like Lithuania beating Russia and being able to take on Canada in hockey. So it was pretty exciting. So that keeps us pretty busy. I used to build telescopes, now I build guitars. Spent a lot of time in scouting. I did point out to Scouts Canada that red shirts are a really bad idea. Have you guys never seen Star Trek? And sure enough, it attracted zombies. I survived, the hat didn't. Yeah, I played some football, or coached some football, and did all sorts of stuff. So we've been keeping kind of busy. But throughout that time, I've been able to keep up with astronomy by using somebody else's telescopes. We still live at the end of the rainbow, so we actually have a good place in the city to do astronomy. But with kids and getting older and so on, it became really difficult to do it. Those of you who have been around a while remember this place. It's a roll-off roof shed observatory, still in my backyard, still sitting there. It generally looked like that all winter. As soon as I dug it out, it would go like that again, so it was a little difficult. And just like me, all my stuff tends to stop working at minus 10°C. I stop working, the telescope stops working, so through a lot of the winter you can't really use it. This is what it looked like inside. I had an 8-inch Celestron. It's actually, this is an early picture because it ended up being 100% computer controlled. I could sit in my house, control it, but it wasn't exactly premium gear, so actually finding stuff was a bit of a hit or miss thing, and you tended to have to go out and fix it and spend a lot of time messing around with it. And it reached a point with the kids and everything, just didn't have time. And staying up late, that kind of stuff, stopped being quite possible. So, got rid of all that and actually spent a lot of time without telescopes. And then discovered something called eye telescopes. And why would I change them from having my own telescope to using somebody else's? Well, getting older, I don't see as well in the dark anymore as I used to. I don't, looking through an eyepiece, I don't really see. So the Mark I eyeballs aren't working that well for me, whereas CCD cameras work really well. So I spent a lot of my time looking through a telescope via CCD versus the eyeballs. At the time when I was using the telescope actively, mosquitoes were like about to carry me away into the night. It's much better now, those of you who do a lot of astronomy now. And again, I stopped working at minus 10 and so does all the equipment. So a big chunk of the year, you're not able to use it. So what I use now is something called eye telescopes. Eye telescopes, it arose from a different network, whose name escapes me right now, but basically it's a network of computerized telescopes all over the world, but now it's pretty much localized in Shining Springs, Australia, at the observatory there. In New Mexico skies, a dark sky area where there's a ton of astronomy stuff. And in certain areas of California, there's all sorts of telescopes, fully automated. You can just jump on, do what you want, jump off with zero restrictions, other than those imposed by the telescope themselves, and we'll tell you a little bit about that. So this is the one I use a lot. It's a Takahashi, 10-inch Takahashi telescope, 250 millimeters, 10-inch, with an S-Big SP10XE ME. Paramount PME mount. It's like a $12,000 telescope on a $12,000 mount with a whole bunch of different filters, and it's generally used for science. You can take pretty pictures with it, like it's got RGB filters, so you can take pretty pictures with it. It works really well. But it's also got photometric BBRI filters that you can use to do photometry. One of the things you need to do in photometry is you need to put different filters in front of the telescope, and the intensity of the light you get from the star tells you more about the star. So if you do a variety of filters, it'll tell you different things about it. I'll show you that later. But because this is essentially $30,000 worth of equipment, it works really, really well. And there's actually guys that run these observatories that keep them working really, really well. So essentially, if you want to take a picture, you enter RA in declination, it centers that in the field, and it'll keep it there for at least 5 minutes. And way longer. But so these are very reliable, and as a matter of fact, although you do pay to use a telescope, you pay by imaging minute. In other words, you get 1 minute of perfect imaging for what you pay for. You don't pay for slewing, you don't pay for calibration, you don't pay for plate solving, all those things. You just pay for a perfect minute of imaging. And for photometry, you're not taking long exposures, so it's actually very cost effective. Now the other one I use, not so much, but I'm using it more and more, is in Australia. It's a Clay wave, 17-inch corrected Kirkham astrograph, very expensive telescopes, these things. It's also on a Paramount, and it has an extremely sensitive CCD camera on it that is very sensitive in infrared, so it's actually got a near infrared emission profile. It holds multiple world record achievements for the most distant objects imaged by amateur astronomers, and it's really good at really faint things. The thing is, if you want to take pictures while the moon is up, forget it. It's extremely sensitive. The bad news is that using these telescopes gets a lot cheaper when the moon is up, because nobody wants to use them, right? So this one you don't use when the moon is up. Some of the other ones I use, actually photometry is very forgiving of the moon being up, so you can get discounted prices if the moon is up. And what I like about this, it actually has a spectroscopic grating in it that allows me to take spectra with this telescope. And we'll talk about that in a bit. This is about a $75,000, $85,000 telescope. So, it is not the most expensive telescope to use. It's actually fairly cost effective. So, what does it look like? Well, when you log in to itelescopes.net, you obviously you need to have an account and all that sort of thing, and you end up on this landing page. And on this landing page, it tells you what telescopes are available. This is it's either my glasses or my eyes, but this might be a little out of focus. It tells you what telescopes are available. Where? So you'll see right now, I took this actually this morning, so you'll see that the telescopes in Australia are active. So if I want to do astronomy in the morning or at lunchtime while I'm at work, I can log on to telescopes in Australia, and it's nighttime there. New Mexico, obviously you can use at night. Astro Campus in California and Sierra Remote Observatory is in California. They used to have telescopes in Nervión, Spain. I'm not sure what happened to those, but they're offline. So basically, you've got two sides of the planet covered. You can do astronomy anytime you want. 99% of the time, I use scripts and pre-scheduled sessions anyway, so I don't actually use the user interface. I run scripts and schedule them. What that looks like is this. So basically, if you want to use the telescope, you can reserve a block of time on the telescope through this calendaring function. And in this case, I've reserved 3 half-hour blocks to do my photometry, to do my pictures for my photometry stuff. And the telescope is reserved for me for that half hour, and any imaging I do during that half hour is taken out of my points total. So every month I pay, at this point I was paying like $19.95 a month, and you're given points, and you can spend those points on the telescope. Most of the time it's approximately $1 an imaging minute, and if you're paying $20 a month, you get 20 minutes of imaging, which doesn't seem like a lot. For photometry, it's actually not bad. I'm on a 40-minute or $40 a month plan now, which is a little more because I was using it a fair bit. And when I'm not using it, like right now I'm not really actively on an observing program, my points just accumulate. So I've got like 300 points, and when I feel like doing something, I've got lots of points to work with. And I don't have a telescope rotting in a shed, not being used, which was the case previously. So what I also do when I reserve this time is I say, okay, run this script, agdraco.txt. And that script basically tells the telescope what to do. It's an automated script. They have script generator user interfaces that allow you to generate these scripts without having to know the details of the commands in the script. But essentially, you can set up the telescope to run scripts, or you can use this control interface. Now what this control interface does is you log onto a telescope. I'm logged onto a telescope right now. If we have time later, we can take some pictures. And you can do a number of things. You can, one-click image basically says, okay, show me what's up today and that I might want to take a picture of. You click on it, it takes a picture of it, and it makes it available to you to download. Super simple. Similarly, if you've got a comet that you want to take a picture of, and I checked that the comet that was mentioned earlier, whose escapes me, is available and we can take a picture. It's not up yet. I think it's may not be up by the end of this session, but or we can run an image series. We'll talk about that in a bit, and so on. So essentially, you can say, okay, let's go take a picture and take a picture, and it will slew to the object, expose, and make that image available to you. Perfect every time. If it doesn't work out perfect, if there's some problem, you send a note to the people that run the place and they'll credit you back your points. So it's perfect imaging all the time. Yep?
Does it do darks and flats?
Yes, it does calibration. Darks, flats, bias. It also plate solves the image. It does astrometry on it, if you tell it to, right? So that it stores the right ascension and declination of the plate with the file as a fixed file. It's a standard astronomy format. So this is your control interface where you can tell it to do some imaging. You can say, okay, I want to go to the plan generator, and you can type in, oh, I want to image M1, get the coordinates for M1, and here's the exposures I want to make. I want to make 10 5-minute exposures in red, green, blue, and luminance, and so on. Right? And it'll do that for you in a completely robotic way. Auto magic, as I say. So, pretty easy to use. It's not exactly a Dobsonian telescope, but if you want to get started with imaging, and particularly if you want to get data that's perfect so that you can learn how to do the processing you need to do things like merge different colors of images and so on, it's very, very helpful to have this, as opposed to having to struggle with equipment and so on at the same time. So this is what a script looks like. And basically, these are comments, but it says upload this to VFLOT, which is the AAVSO site to do analysis. So I want 4 images, 30 seconds each, binned at 1 in each of these 3 visual, blue, and infrared filters. So take basically a total of 12 images with these filters of this object. And this is AG Draco, is a variable star, and this is the right ascension and declination of that star. So it goes, points with it, takes those pictures, downloads them, and it actually uploads them to the site that I use to analyze it. I'll show you how that works in a bit. So on the back end, you'll see a lot of familiar software. This is actually an image that you can get from the user interface. It tells you what's going on in the back end. So we've got Maxim DL, and we've got the sky, and we've got focusing software, and this is the observatory control software, all talking together via a protocol called ASCOM, all pre-set up and integrated for you. This is the kind of stuff that you would need to do to set up an automated telescope for yourself. This is the kind of stuff I did, except I couldn't afford a lot of the software, so some of it tends to be expensive. But all of the software in the back end works together and then shows you that nice pretty web interface. So is it expensive? Well, it depends. If you're me, where you might have an observing program where you want to take pictures of some stars a few times a week, a few times a month, and analyze the data, and otherwise just explore science, it's extremely inexpensive. If you want to do some light astrophotography, it's quite inexpensive compared to the kind of equipment you would need to do that well for yourself. Right? So equipment, I don't know if Kevin's here, I don't know if he'll admit how much he spent on his equipment, but some amateurs might spend $20,000 or more on their rig. I was more on the $5,000 end, and I got kind of $5,000 results. It worked, but it didn't work all that well. I spent a lot of time messing around with equipment, and the number of minutes of perfect imaging I got was quite low compared to the effort expended. And of course, once kids came into the picture and stuff, I didn't have the time to expend that effort, so it was a moot point. So what you have to say to yourself is, if you're getting into astrophotos, astroimaging, how many perfect minutes of imaging do I get out of my telescope any given year? So you might say, okay, well, I'm out 12 hours a month, which is a fair bit. Times 12 months, of course, those 12 hours a month might be compressed into summer months and spring and fall. How much do I spend tearing down, setting up, and messing around with equipment? Maybe half of that. So you might get 4,300 minutes of imaging time per year of perfect imaging time, if your setup is good enough to support imaging. So that's 350 minutes a month. That'll cost you $200 or $300 using eye telescopes. So if you don't have the time and expertise and money to buy that $5,000, $10,000 worth of telescopes to do imaging with, this is a good alternative. If you're spending 8 hours a week doing imaging, and you've spent a lot of money on your equipment, or you're willing to spend a lot of money on equipment, or if you just like messing around with equipment and being out under the stars and doing this for real, then obviously this isn't nearly as attractive to you. So you have to make that determination yourself. For me, it's a no-brainer. So if you just want to get imaging, your break-even is 2 to 8 years on your own telescope, or you could just pay as you go using an eye telescope, which is really nice. And you're going to use equipment that's probably orders of magnitude better than you could ever put together yourself within a reasonable time. So it's a monthly subscription. It's starting as like $19 a month, goes all the way up to infinity, obviously. You can spend as much money as you like. I spend about $40 US a month on my subscription. If you don't do any imaging, the points just accumulate. And there's no upfront cost for gear. So that's eye telescopes. It's pretty easy. You're just renting somebody else's telescope. It's kind of like the cloud in computers, right? We'll put everything on the cloud. Well, the cloud is just somebody else's computer you're renting, right? You just don't have to have the expertise or money to put together something like that. Any questions? Yeah.
So if you do imaging, it presents to you a series of FITS files, and it'll present you with darks and flats, and then you can process them in your own.
Well, it'll calibrate your images for you.
Okay.
So the lights you get are pre-calibrated, unless you tell it not to, right? There's reasons why you wouldn't. So you download via FTP all of those FITS files, and then you can process them further. So basically, they're perfect images that you can then process further and bring them into nebulosity or something and do the LRGB synthesis and all that kind of stuff. And do the sort of artistic part of creating astroimages. Yeah?
You mentioned how this is an attractive option for, say, people who don't want to buy all the equipment, but they're beginners and they want to try it out. How much of a learning curve is there? Does the website have any tools for tutorials?
As a matter of fact, the website has tons of videos on the basics. I don't think anybody who has an interest in astronomy would have a lot of problems logging in and doing a one-click image. especially like T3 in New Mexico is actually a single shot color camera. So you can start, I actually, a few months ago, I was sitting in the meeting here with my iPad, taking a picture of the Horsehead Nebula. Unfortunately, I don't have it handy, while I was sitting here listening to a presentation. Right, and it turned out really good. It's my wallpaper on my computer at work. Right, so it's snapshot easy. Right. Now, if you start doing more sort of extensive stuff where you need to do a lot of processing, that sort of thing, then you need to learn how to do that. But there's videos, and as a matter of fact, you can pay to have instruction. They have master classes that iTelescopes put on, which I didn't know, but somebody pointed out on the list. You can actually take master classes in imaging and processing of images through iTelescopes, using iTelescopes, so it all ties together. So, it's not hard. We can do one. I'll hurry through. How am I doing for time? Oh. There's a half hour between you and pizza. So, what is a variable star? This is, we've touched on this a little bit today. A variable star is a star that varies in intensity for some reason, right? All stars are slightly variable. The sun is slightly variable. It will vary in intensity over time for a variety of reasons, for a variety of mechanisms. Usually the variable stars that we look at in the sky right now are varying in a very obvious way. Although we've sent out a number of satellites that have been analyzing the sky, looking for variable stars, and have been finding a mittful. Most stars, I would say, have some level of variability that's detectable. Now, there's two types of variable stars. One is intrinsically variable. In other words, it's doing something itself. Or there's extrinsically variable stars where some other force is acting on the star, or it's a system of stars. So one of the most famous and very useful types of variable stars is Cepheid variables. And you may have heard, if you've been looking at the history of astronomy, you may have heard the word Cepheid variable because in the early part of the 20th century, Cepheid variables were instrumental in figuring out the distances to extragalactic objects. Because a Cepheid variable has a very interesting property where the period of its variability is proportional to its absolute magnitude, how bright it really is. So if it's varying at a certain with a certain period, that tells you how intrinsically bright the star is. If you know how intrinsically bright the star is, if you were standing right next to it, God forbid, then if you use the inverse square law and you look at how bright it is visually from the Earth, you can tell how far away it is. That's really important if that star happens to be in a different galaxy. So one of the things that a lady named Henrietta Leavitt, and I think the 1920s did, is she's discovered on some old plates from various observatories, probably from, wasn't Palomar at that point, but some of the observatories in the early part of the century, she noticed that stars were varying in the Andromeda Galaxy and the Magellanic Clouds. And these were Cepheid variables. And because we knew Cepheid variables from our own galaxy, and we recognized their intrinsic property, we can now tell how far away those galaxies were. And it blew our minds, because they were not in our galaxy, they were outside our galaxy. At that point, they didn't even know that. Right? There was a big argument, actually a big debate. Harlow Shapley, a famous astronomer, and some other guy whose name I forget, were debating in Washington, D.C., are galaxies inside our galaxy and they're just nebula, or are they outside? Well, Cepheid variables were the yardstick that definitively proved that galaxies are outside our galaxy. Very, very useful. And we know a lot about how these things work. Cepheids are really interesting because they're intrinsically variable, which means they get brighter and dimmer and brighter and dimmer. And it's interesting to try to figure out why that's happening. Because a star will flare up and get dimmer, and flare up and get dimmer on a very regular cycle, like a perpetual motion machine, except there's no such thing as a perpetual motion machine. So there must be something happening in the star. Well, we know when a star blows up, it's because it's getting hot, and the radiation pressure is pushing the star up. And we can guess it's like a pendulum, right? So this radiation pressure pushes the star's envelopes out, and then the gravity pulls it back in. And because it's falling back in, it actually overshoots, it compresses the core of the star, which gets really hot again, and pushes it out again, right? But just like a pendulum, it's not long before that will wind down, right? It gets the mechanism that keeps it going will eventually come to equilibrium. That's just how things work. But Arthur Eddington, who was famous for actually proving that relativity, or providing a proof of relativity, this is early in the 20th century, figured it out that some layers of the star actually become opaque to radiation at certain temperatures and densities. So what happens is the star compresses, 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 and then the lid goes on the pressure cooker for a little while, and it sits there and percolates until it's got enough energy to overcome that, heat it up, it becomes transparent to radiation again, and out it goes. And there you have the mechanism that keeps the perpetual motion machine going. Just like any other perpetual motion machine, they're cheating, right? So Cepheids are very interesting. Variables, if you look at the GBCS, which is the General Catalog of Variable Stars, because there's a catalog for everything, you'll see there's 5 major types. Eruptive, which is generally intrinsic. The star goes poof, right? The image you see there is, I'm going to get this wrong, V858 Monocerotis, V858 in Monoceros, the constellation. That's a star that erupted and blew off a whole bunch of photons. That stuff that you see around that star is not stuff that's been blown off the star. Really, it's gas and dust in the interstellar medium. The light from the star traveling at the speed of light is hitting those regions, lighting them up, and that's how you get an effect. Beautiful effect, like the 858. I think it's 858. It's a variable star. It's an eruptive star, and that one really went off. You've also got cataclysmic variables. You've got systems of stars that are orbiting each other, and they're losing. One star might be losing mass into the other one. You might have a star that's big and has a lot of material being orbited by a white dwarf or a neutron star or a black hole, and those are cataclysmic because the material flows into the star and eventually it reaches a certain point and boom, right? Now supernovas happen that way, but you also get these novas and dwarf novas and symbiotic stars and so on. You've also got variable stars that are variable because of rotation. So you've got a really bright star and a dim star, and they're rotating, and the dim star passes in our line of sight, the star dims. It passes our line of sight, the star gets brighter again. So, lots of different types of variable stars. And part of the fun, this is where I say some people would find this stupefyingly boring, but part of the fun is figuring out what kind of variable it is and how it works. So the star that I was looking at not long ago, that I'm not looking at anymore because I'll tell you why, but I was looking at a star called AG Draconis. It's in the constellation of Draco. And it's one of these orbiting binary stars. Okay? It's symbiotic. One of the stars is an orange-red star, a large orange-red star, a giant star. It's about 3.5 to 5,000 Kelvin, not too hot. And it's got a white dwarf, which is at 80,000 Kelvin, which is quite hot. And they orbit each other. Material is passed through the area between these stars, the Lagrange point, and forms an accretion disk. So what's falling into this white dwarf, some of it misses, so it kind of goes around again, and it forms this disk, and occasionally this disk will blow up. And this is what we see from here as a burst of light and an increase in its magnitude. And this is what we were watching for. So this is where AG Draco is. It's a 9.8 magnitude, so it's not visual, but you can see it in the telescope. It's right here between Ursa Minor and Draco, right there. So, remember I was talking about VFOT, which is, or VFOT. This is a tool that the American Association of Variable Star Observers gives its members, and makes it super simple to analyze this stuff. So, when I come into work or at lunchtime, I've got some data that's come down. This is pretty hard to see. These are image files, and iTelescope just downloads them to VFOT for me, so they're waiting for me. And what I do here is, first of all, I stack them. What stacking does is it improves the signal-to-noise ratio so I get better data. Just like you stack pretty pictures to make them look nicer, you can stack scientific data to improve the signal-to-noise ratio. So what I do is I stack, I've got three filters, and I've got 4 images per filter, so I'm stacking those 4 images, which will leave me with 3 stacked images, 1 in each color filter, 1 in infrared, 1 in blue, and 1 in visual, which is basically green, right, because we see it in green. So once I've stacked those things, I can look at them in this interface, and then I can tell it, okay, show me the variable star, and now show me some comparison stars. And this is called differential photometry, and what you're doing is you're basically looking at an image of a star, comparing it to other stars that you already know how bright they are, and that will tell you how bright the variable star is. Now, you can do this visually if you want to look at a star like Mira or Algol or one of these bright visual variable stars. You can look at it and say, well, you know what, I know that the stars around it are certain magnitudes, so I can guess pretty well, pretty easily, that the magnitude of the star is somewhere in that range, and you can compare them. What we're really doing here is we're doing that in a very rigorous way, so I can get within 0.02 of a magnitude error using CCD cameras. Is it 0.2? Yeah, 0.028 magnitude is the error I'm getting, which is actually pretty great. So once I've done that comparison, it dumps down to a file. I upload that file to the AAVSO, and I've now recorded an observation. It has my name on it. People can go look at it. They see Tiger, and they know it was me. Nerd cred all over the place. Eventually, it'll be done. Oh yeah, that's the end of the picture, sorry. So that's an imaging run for doing photometry on a star. You're basically 3 different filters recording 3 different magnitudes through those filters, and the difference between the magnitudes in those filters give a lot of information to scientists on what color the star is, and that color and intensity can give them a lot of information about what's happening with the star. So that's boring, but that's what the file looks like. The end result is a light curve. This is a light curve for AG Draconis, very recent one. And the reason we were looking at it, the AAVSO sends out bulletins saying, hey, this star is going to do something interesting probably. Could you watch it for us so that we can get data on it? And then scientists can download that data and figure out how the star is working. And so, round about here, they send out a circular, it's called, and all of a sudden people started observing in visual, in blue, and in infrared this star. Now, if you look at, wrong button, if you look at my observations are now superimposed, you can see the little crosses are my observations. Obviously, I started looking at the right time because I actually was able to capture the eruption of the star, which happened right here in the 3 different colors. So what they do,
Hey, Corp, just
Yep.
out of curiosity, what is the, can you go back to this one? What's the actual, like, so from like peak to trough there, what's the time you figure? I mean,
this,
it's on the order of months, right?
it's on the order of less than a month. I think this whole thing is, what is it, from 2017, 2016, October through July, end of July. So it's not a long time. Which is part of the reason why this is a good star to look at. This was the first star I actually did a really rigorous observations for. Now, if you look at this star over time, the light curves are very informative, and the AUVSO has been doing this since the 1800s. So we have data on stars going back centuries, right? And this data gives astronomers a really good idea of exactly what this star is doing, which is interesting. So if you're doing photometry, picking candidate stars and learning, and then watching them do it is pretty cool. And it's pretty, you're actually not only enjoying yourself, but you're actually helping scientists by providing data that then they can put into their mathematical formulas and figure out actually what's going on with a star, which tells us more about the universe. So photometry is pretty cool, I think. So, other stuff you can do. Some other projects I've been working on. There was an occultation. In other words, a planet passed in front of a star in July. I think it was July. No, it was August 15th. I was in Saskatoon at the Lacrosse Nationals at the time, but was able to take some pictures. Not with that telescope, with the other one. An occultation is basically, for example, in 19 July 2016, Pluto passed in front of a faint star. And what this does is, by measuring the intensity of the light coming from that star, they can actually tell stuff about the atmosphere of the planet, the composition, what it looks like. So, and what you see, obviously, is you see the star, then you see the star disappear, then you see it come back. And what you get is a light curve that looks like this. And if a whole bunch of people are all imaging it at the same time, you're going to get a lot of data points. Even if the individual is not getting a lot of data points, collectively, you're crowdsourcing this thing and getting a whole bunch of data. Now, you can't see that very well. In August 14th, 15th, I used the T5 telescope, that 10-inch Takahashi, to take approximately 70 images of Pluto passing in front of this star over about 20 minutes. So this was about 11:30 at night to about, well, 11:20 to about 11:40, right? 70 images. Now, because I needed to take the images fairly quickly, the 2-second exposures over 20 minutes, as many as possible to capture as many data points as possible. I asked, don't calibrate it, so it didn't do any calibration, so I had to do that manually. Don't do any plate solving, because I have to do that manually. All of the processing that it would normally do takes time that would take time away from imaging, right? So all of the processing that I have to do on 70 images is still ongoing. So I haven't got a picture to show you. I actually was hoping to try to get a picture, like an animated GIF of the star going down, going away and coming back, but didn't manage it. Of course, I started it this morning, so. But still, the point I'm at now is all of the images are calibrated and they're plate. Most of them are plate solved, so I'm still doing data reduction on it. So it takes a while. I'm using a piece of software called Astro Image J, which is fantastic if you're trying to do science work. The problem with Nebulosity is the software I use, Nebulosity 4 is the software I use for pretty pictures. The problem is it tries to stack things all the time. It figures you want to stack things. Unfortunately, you don't want to stack this because that'll make a blur and it won't give you any data. So Astro Image J is really, really good for this kind of work if you want to do batch calibration and analysis of images for things like photometry. And actually, I took a course with the AAVSO on exoplanet transits, and that was the software that I used. So the other thing you can do is spectroscopy. How can we do it for time? I can go all night if you want. Oh,
10 minutes.
a little bit of time. So what spectroscopy is, light is the only thing we have to tell us about the stuff in the sky, right? The only thing we're getting is light and radiation. Light being, the whole spectrum. So the way we use light to figure out what's happening is actually really amazing. So for example, using a spectra of a star, you can very easily tell how hot the star is. Very easily. Stars are black bodies, they emit radiation, and there's a peak in that radiation curve that tells you how hot it is with a very simple formula. I did that demo years ago. So what it also tells you is if you've got a variable star that's erupting, look at that a little closer, this is A.G. Draco, yep. So it tells you what the spectrum looked like when it wasn't erupting, and then you can look at the spectrum when it is erupting, and it tells you what's happening with the elements in that star, because every element has a very characteristic either emission or absorption line in a spectrum. If nobody's seen a spectrum, sorry, I should have got a picture of it. Actually, I do, right here, thinking about it. So this is a spectra, right? And what these prisms do, and what that X-ray satellite did, is it smears out the light that's coming from the star, and there's going to be little gaps in that spectrum because different elements absorb different wavelengths of light. So there's going to be bright spots, and there's going to be dark spots, depending on whether it's emitted or absorbed, right? So spectrums are very useful to tell you what the stars are actually composed of and how that changes. So if we back up a bit, you can see that there's a huge spike in hydrogen alpha between the 17 March and April 29th when this thing is in eruption, and huge spikes in helium, and it tells you a lot about the composition of the star. Again, what does that mean? I'm not entirely sure, to tell you the truth, but it's important to scientists, and they can figure stuff out based on that. So spectra are really cool when you've got an event happening. It's really cool to get a spectra that tells you how things are changing in the star. So on T17, the telescope in Australia that I use, they have one of these little things. I used to have one of these on my telescope as well. And what it does is it takes the star. This is a star trail that it's actually turned the drive off so it trails a bit, and it shows you the spectra of the stars. So very handy. You can cut and paste that little square, put it in an analysis program that converts intensity of light to a bar graph, and you can actually do things like tells you what color it is, tells you what the primary constituents of its atmosphere is, and so on. Now, it ain't going so well with T17. I think this is a problem that they're working on, so I haven't really gotten good spectra from T17 yet. I've tried to do it when the moon's in the sky. Forget it. It's not even as good as that. But you'll see as well, in a very crowded star field, all of these spectra kind of merge together. So that's something I'm experimenting with. Hey, but I got a $75,000 telescope to play with, and I'll experiment. It's It's cheaper to experiment on somebody else's telescope, that's for sure. So the other thing that is something I want to start experimenting with is exoplanet transit. And that's a lot like variable stars that are orbiting each other, right? So the planet in this case goes around the star, passes in front of it, and the light dips. And we actually have a bit of a picture of what it doesn't look like. So this is actually an image of actual planets orbiting another star. You're not going to get this with any telescope that we have access to. It was moving. Let's try it again. Oh, there they are. So what they've got here is they've got a little mask in front of the star, and they can see the planets going around the star. We have to use methods that are not quite as direct as this to see other planets. What we have to do is we have to detect the planet passing in front of the star, because the star just happens to luckily be edge on to us. The plane of the rotate, or the plane of the orbit happens to be edge on to us. So what we can do is we can take photometric measurements, just like we looked at on that VFOT software. We can take photometric measurements of the magnitude before the planet enters the star's limb. We can see how the light goes down, and once it leaves, we can see that it's gone back up again. Exoplanet transits are easily detected by amateur telescopes, and that's a project that I want to embark upon. It is also a project that is not suitable for eye telescopes, because transits take hours or days, and reserving an eye telescope for hours and days will get a little expensive, right? However, the AAVSO actually has a network of telescopes, robotic telescopes, that you can request time on, very similar to like a university telescope where you have to request observing time on it to run a particular program. So that's probably how I'm going to get some data on exoplanet transit. The AAVSO had a really good course on how to do this, including using the software to actually get your data out. So this is something that I want to experiment with. So some of the other tools that you have, exoplanets, well, any variable stars, it's sometimes difficult to figure out what to look at. Often AAVSO will send out a notification saying, hey, you want to look at AG Draconis because it's going to do something really cool. And you can start looking at it. Sometimes you can get a list of stars that are easy to look at if you're just starting. You can get a book, David Levy put out a book, which is heavily about observing visual variable stars, that I highly recommend for starting if you want to use your eyeball or binoculars or a small telescope. And AAVSO has a lot of utilities to use to figure out what you want to look at. The target tool is fantastic. So you can pick what kind of object you want to look at, and it gives you a list of objects that are actually doing interesting things right now, or have an observing program that people are pursuing, or so on. So I assume you'll be able to get that URL. So here's some books that you'll find interesting. The Levy book is really, really good for beginners. It explains what variable stars are, and for each type of variable star, it gives you examples that you can go out and look at right now and start watching. Because, a lot for Mira, for example, Mira, the Wonderful, was the first variable star that was detected. I think it's in Perseus. Is it Perseus? So Mira will brighten up to quite bright and fade to virtually indetectable over a period of time. So visually. So that's why they figured out, hey, something's going on with this star. Algol is another one, where they get brighter and they get dimmer. What's going on with that? So if you look in this book, it has a lot of information on visual variable stars and getting started. This one is a lot deeper, and is if you're interested in using CCDs to observe variable stars. It's kind of the Bible. This one is also very good. This one is really neat because it's not just variable stars, it's all kinds of different ways that you as an amateur can get involved in providing data to professional astronomers and working with professional astronomers. It's very common these days for professional astronomers to include the amateurs who provided data to them in their credits on their papers. It's a major nerd credibility there too, right? But you're basically helping move the science along, and it's kind of cool to have your name on the paper, right? AAVSO actually sends you an email. Anytime a scientist downloads your data, you get an email that tells you your data's been downloaded. So that's pretty cool. So Sky Azure Laboratory also talks about photometry, it talks about spectroscopy, it talks about all sorts of scientific things you can do with your telescope, as well as just looking at things. And finally, this one is a freebie, astrodentist.com, and this is the manual for observing exoplanet transits, planets circling other stars. So it's a freebie. It's very dense, and it's mostly about how to use Astro Image J to reduce data. So it's stupefyingly boring, probably, but yeah, it's a good book. It's the manual for the course I took. I think that's it. I think I did keep you from pizza for more than 1 minute, so it's 9:59. Any questions? Last questions? Yeah?
Forward, a question. So the reduction of the data, so you've used your eye telescopes, and you've taken your exposures, visual, infrared, etc. And does the software actually do the magnitude estimate for you?
VFOT does.
Yeah, so VFOT
Yeah.
does, right?
So what you saw on VFOT is you look at the star, the image of the star, and you look at the comparison stars. AAVSO actually requires that you designate a check star, which is for sure not variable, because comparing a variable star to a variable star is obviously not a smart thing to do, because they'll be different, right? So you create a check star, and it analyzes the flux from all of the different stars in that image, and then does an estimate of the flux coming from that star, and that's your magnitude estimate. It's very, very exact. When you get the signal-to-noise ratios that I'm getting from the eye telescopes, the error level is very low. Some of the other observations you saw on that light curve were scattered all over the place. Those were less exact observations from various observers, because some people have a 0.1 or 0.5% magnitude error in their estimates, right? Because of the way they're doing it. So yeah, VFOT, the combination of eye telescope and VFOT gives you a complete photometry tool set.
Excellent.
Yeah?
Are there plans in the future to have, I guess, a better resolution for some of the spectra? I know you the star analyzers on that T17, but are they looking at putting like these?
If I won a lottery, I would buy a 20-inch plane wave on a plane wave mount and put a spectrometer on it. So we're just waiting on somebody winning a lottery. Sort of. It's kind of, the pros have the tools. Generally, if a star goes into outbursts, there's some pro in an observatory with a spectrometer, with a slit and all that kind of great stuff that's measuring that. So it's probably not a huge priority. I think spectroscopy is incredibly cool. There's tools like the L-high-res, and there's a few spectrometers which are within reach of amateurs, a few $1,000s. So it's not impossible that somebody will actually foot the bill to do that. With eye telescope, you'll notice there's a lot of telescopes in those buildings. Those are not all eye telescopes. Those are owned by other people that are run by eye telescopes. So seriously, if I won a lottery, I'd buy a big telescope, put an L-high-res on it, and put it in New Mexico, and be able to take spectrum. But like I said, nobody's won a lottery yet, I guess. So no nerds have won lotteries yet. Okay, thank you very much.
Okay, yeah, that was a meeting. We will continue They texted me about a half hour ago to say my reservation's coming up and that my plans are changing. I should let them know. If more than 25 of you show up, my plan is changing. But should be okay. Yeah, so thanks everyone for coming out, and see you all next month.